This will be a walkthrough of the AQA GCSE Combined Science Chemistry 2023 Higher Tier Paper 1. Question 1. This question is about carbon dioxide. Carbon dioxide is soluble in water and forms an acidic solution. Which ion makes this solution acidic? Well, let's think about some examples of acids. HCl hydrochloric acid, HNO3 nitric acid. These both contain hydrogen, which is what makes them similar, and what makes them acids. So the ion that makes the solution acidic is the hydrogen ion. Instead of writing, though, hydrogen ion, we could just write the symbol, which would be H+. 1.2. Name an indicator that could be used to test if the solution is acidic. Give the result of the test. So an indicator, it could be a chemical, or our other method of testing would be some sort of piece of paper. So the common indicator that can be used to test if a solution is acidic would be universal indicator. Now, if we were to use that, what color should it turn? Well, remember your pH scale. If something is acidic, very acidic will be red, and slightly acidic would be orange. So the result of the test then, if something is acidic, it would turn red, and that would be acceptable. If we didn't mention universal indicator, then we could mention our piece of paper that we could use, which would be litmus paper. But the color of the litmus would actually need to be blue. And then if we dip that into a chemical solution that's containing an acid, it should then also turn red. Figure 1 shows the mass of carbon dioxide that will dissolve in 1 decimeter cubed of water at different temperatures. Here's our graph. X-axis temperature of water in degrees Celsius. Y-axis mass of carbon dioxide in grams dissolved in 1 decimeter cubed of water. If we look at the shape of the line is going down. So using our axis, this can tell us then that as the temperature is increasing, the mass of carbon dioxide in grams dissolved in 1 decimeter cubed of water is decreasing. 1.3. How does the solubility of carbon dioxide change as the temperature of the water increases? So we have to be looking at this direction in terms of our x-axis, what's happening to the solubility. Well, if the carbon dioxide is dissolved more, that would mean that it would be more soluble, and then that should mean that it should be higher on our y-axis. But you can see as we get to 60 degrees that that mass is actually below 1 gram. So that actually means then that the solubility is decreasing. Carbon dioxide dissolves in water to form an acidic solution. How does the pH of the solution change as the temperature of the water increases? Well, the statement says that carbon dioxide forms an acidic solution when it's dissolved in water. So pH, if the pH is decreasing, and that means goes from 5 to 1, for example, that means that it must be getting more acidic. if the pH of the solution is changing and the carbon dioxide from our previous question is decreasing in its solubility, that means that there'll be less of the carbon dioxide in the solution. So that means that it can't be getting less acidic. So it cannot be decreasing. And it's not going to change. So that means it's increasing. Calcium carbonate reacts with hydrochloric acid to produce carbon dioxide. The equation for the reaction is shown here. What is the state symbol X in the equation? So here's the state symbol X, and it's next to water. Well, water can't be aqueous because something would need to dissolve in water for that to be the case. We've already got one of the gases produced, and that's carbon dioxide, so it will not be that. The water's not going to be a solid because it's not going to form ice, so it can't be that either. So our water must be then a liquid. (1.6) Figure 2 shows equipment a student used for an investigation. Let's identify the piece of equipment that they've shown us first. We have first a measuring cylinder. Then we have a conical flask. Underneath our measuring cylinder, this would be a gas syringe, which is already labeled. And then lastly, we have a balance. Now, before we look at the question further, let's remind ourselves what each of these pieces of equipment will do. A measuring cylinder will measure the volume of a liquid. The conical flask can also measure volume of a liquid, but it won't be as precise as the measuring cylinder. So it'll really be there to carry out our reactions, hold them, mix them. Our gas syringe is there to measure the volume of gas that's produced from a reaction, and the balance is there to measure the mass of a solid. The student investigated the volume of carbon dioxide produced when different masses of calcium carbonate react with hydrochloric acid. Describe a method the student could use. 6 marks. So we're describing a method. Again, like before, we need to mention our variables. So let's start with those. Independent variable, what we change. Dependent variable, what we measure. Control variable, what we keep the same. Now this question is very similar to your required practical when you're trying to measure the temperature change. Now if you look at it, it's actually not asking us to measure temperature change, but we are dealing with something that we're adding, that we're changing, and another chemical that's involved. So let's read the statement again, and let's see if we can identify some of these variables now. So it said different masses of calcium carbonate. So remember, our independent variable means change, so that is what it should be. It should be the mass of calcium carbonate. What do we want to measure in this experiment now? The student investigated the volume of carbon dioxide produced. So volume of carbon dioxide produced will be our dependent variable. Now what do we want to keep the same now? Something that could affect the volume of carbon dioxide produced. Well, that would be the temperature. So maybe we could mention something that we could use to keep the temperature the same. What else could change the volume of carbon dioxide produced? It's got to be the hydrochloric acid, something about it. The two things that we want to probably keep the same about the hydrochloric acid are its volume and its concentration. So let's just state both of them, and we should be happy to start describing our method. So what's the first thing that we want to do then? Well, we're going to be changing the mass of calcium carbonate, so we need to measure that mass now. So we're going to measure the mass of calcium carbonate using the balance. Now, remember that we want to change the mass of calcium carbonate, so we want to probably use a certain mass of that calcium carbonate, so we can specify the mass if we wanted to, but for now we can just write certain mass. What we would then do is transfer this known mass of calcium carbonate to the conical flask. So we've got the conical flask, it's got the calcium carbonate in there now. What's the next thing that we'd have to do? We can't start the reaction until we add the hydrochloric acid. So we need to measure a certain volume of hydrochloric acid using a measuring cylinder. Right, so we've got a volume of hydrochloric acid, we know what that is. We are then ready to start the experiment. However, at this point, we want to act very quickly. Remember what we're trying to measure? We're trying to measure the volume of carbon dioxide produced. Now remember, in our equipment, we're going to be using a gas syringe. How is the gas syringe going to work? If you look at the end of the gas syringe, there is a bung. Now the point of the bung is to secure the top of our conical flask. So the bung will go inside the conical flask, and then that would mean that no gas can either enter or escape through the bung. The only way that the gas that's produced can escape is through the tube of the gas syringe, and then it would push our plunger to the right. And because the gas is getting collected there, there's a scale that you can see on the gas syringe, and then that's how we record our measurement. So what we want to say in our method now is that we want to attach the bung to the conical flask immediately after adding the hydrochloric acid. So add hydrochloric acid to the conical flask and then attach the bung immediately. Now, at this point, there are two things that we could do. We could A, wait for the gas syringe to reach a specific volume, and then we stop, or we leave the gas syringe for a certain amount of time and then record the volume of gas that's produced in that time. So what we'll do is then in this case we'll write down record volume of gas produced. Obviously we know that the gas is carbon dioxide in a specific time. Okay, what do we do after we do that? Obviously, once we recorded it, we then can repeat the investigation. Now remember, working scientifically, if we're not happy or not sure about the result that we've just gotten, we could repeat it at that same mass, and then again, essentially, we could get a mean if we do it twice. So we could say repeat investigation with same mass of calcium carbonate twice and calculate mean. But then what we definitely want to do after we've done that is repeat the investigation, but with a different mass of calcium carbonate. And there's our answer. We should get 6 marks. Question 2. Lithium hydroxide reacts with sulfuric acid to produce lithium sulfate. The equation for the reaction is shown. What type of reaction is this? 2.1. So we've got lithium hydroxide, as they told us. We know that this is a base. Hydroxide would be a base. We've got sulfuric acid, so we've got an acid. So we're reacting an acid and a base. Now one of our products is water. What's our other product? Well, the rule is whenever you react an acid and a base, you should always get a salt and water. So what type of reaction is it when an acid and a base react to form a salt and water? Well, it is called a neutralization reaction. Now, why is it called that? A base is going to have a pH value between 8 to 14. An acid is going to have a pH value between 1 and 6. Water is going to be neutral, pH of 7, and the salt is going to be neutral, pH of 7. So you're taking two things which are not neutral, reacting them together, and you're making two products which are both neutral. And that's why it's a neutralization reaction. 2.2. Calculate the relative formula mass of sulfuric acid. Formula is given, and the relative atomic masses of hydrogen, oxygen, and sulfur are all given. So, to find the relative formula mass, we need to add up the relative atomic masses from what is in our formula that we're interested in. So let's take first hydrogen. We know the relative atomic mass is 1, but looking at the formula, there are 2 atoms of hydrogen. So it would be 1 times 2. Remember, we're adding, forget the formula mass. So we look at sulfur now. In our formula, there is only 1 sulfur atom. The relative atomic mass of sulfur is 32. So we're going to add that to 32. And then, looking at our formula, we've got 4 oxygen atoms, and the relative atomic mass of oxygen is 16. So that would be 16 multiplied by 4. So simplifying this now, 1 times 2 we know is 2, plus 32, that's going to be 34. And 16 multiplied by 4 is 64. So 34 plus 64 would be 98. That's the relative formula mass of sulfuric acid. (2.3) Calculate the percentage by mass of oxygen in lithium sulfate. The relative atomic mass of oxygen is given 16 again. But then they've given us the relative formula mass of lithium sulfate, which is 110. Give your answer to two significant figures, 4 marks. Right, so we need to find the percentage by mass of oxygen lithium sulfate. So to find the percentage of an element in a compound, what we must do is find the RAM of that element and then divide it by the RFM of that compound and then multiply it by 100. So the RAM of that element divided by the RFM of the compound multiplied by 100. So again, oxygen is the interested element for us. So we've got to use the relative atomic mass, which is 16. However, just like before in the previous question, there are 4 atoms of oxygen. So it would be 16 multiplied by 4 again, and that would be 64. The RFM of the compound is given to us 110. So we're going to just take 64 and divide it by 110. We'll get an answer now of 0.58. Multiplying that by 100 now, that should just give us a value of 58%. Now, because we've done some rounding, it would be a bit easier. But if we use the calculator, we would probably get a slightly different value than 0.58. So when we multiply by 100, we get a slightly different value than 58%. So that's why we need to give our answer to two significant figures, but it will definitely be 58%. (2.4) A solution of lithium sulfate contains 0.30 grams of lithium sulfate in 25 centimeters cubed. Calculate the concentration of lithium sulfate in grams per decimeter cubed. So you can see, if we take our values with units in the question, we've got our mass in grams, and that matches what we have in our unit here. But our volume that's given to us is in centimeter cubed, and that's not the same as decimeter cubed. So the first thing that we want to do then is convert our centimeters cubed to decimeters cubed. So to do that, we must divide by 1000. So we're taking 25 centimeter cubed, dividing that by 1000, and we come up with an answer 0.025 decimeter cubed. How do we calculate the concentration? Well, our formula for concentration equals mass divided by our volume. So if our mass, we know, is 0.30 grams, our volume in decimeter cubed is 0.025. What we do is put that into a calculator and we get a concentration of 12 grams per decimeter cubed. Question 3. Sodium is in group 1 of the periodic table. Sodium reacts with oxygen to produce sodium oxide. Balance the equation for the reaction. So we have to put a value in front of sodium and a value in front of sodium oxide. So when balancing equations, what we should try to do is write out the atoms that we have on both sides of our equation, and we're looking to see which numbers are not equal. So for sodium right now, we have 1 atom. For oxygen on our reactant side, we have 2 atoms. For sodium on our product side, there's a 2 after our sodium, so that means we have 2 atoms of sodium. But for oxygen, there is no number after it, so we only have one atom of oxygen. So the numbers for both sodium and oxygen are uneven right now, so it's not following the conservation of mass, and that's what Wellington equation is all about. So when adding numbers in front of our elements or compounds, the smallest number that we can add is a 2. So let's try and add a 2 in front of sodium and see what happens, because we need to get that number up to the 2 on the right hand side. So putting a 2 in front of sodium, it will only change the sodium, so it will now make that a 2. So our sodium seems to be balanced now. However, the problem is the oxygen on the right hand side. It's not enough. So again, let's change the oxygen now. So we can only do that by putting a 2 in front of our sodium oxide. So what does this mean now? Well, for our oxygen, it's going to be 2 multiplied by 1 oxygen atom. So that means that it will be 2. However, we have to then multiply it by how many sodium atoms we have. So there are 2 sodium atoms originally, but multiplying it by 2, so that means we now have 4 sodium atoms on our product side. So we're definitely happy again with our oxygen atoms, but the problem is the sodium number on the left hand side. So we need to increase that so it will equal 4. So because the oxygen atoms on our reactant side are not going to be interfered with, all we then would need to do is change our sodium number on our reactant side to 4, and that should work out for us now. (3.2) Explain what happens to sodium atoms and to oxygen atoms when sodium reacts with oxygen to produce sodium oxide. Answer in terms of electrons. 4 marks. So we have to think about this reaction between sodium and oxygen. Well, we're making a compound, sodium oxide. We need to think about what type of bonding now would be between this compound. Well, we've got sodium, which is a metal. We've got oxygen, which is a non-metal. So, non-metal and metal is ionic bonding. So, we then have to realize that if it's ionic bonding, it means that one atom is losing electrons to become an ion, positive ion really, and one atom is gaining electrons to become a negative ion, and then there's an electrostatic force of attraction between them. So, what's the rule then? Metals always form positive ions, so that means that they are losing the electrons. So, the first thing that we would need to say then is sodium is losing electrons. Now, there are 2 sodium atoms. Remember that sodium is in group 1 of the periodic table. So for it to become stable and for it to have a full outer shell, it would only need to lose 1 electron. Oxygen is actually in group 6 in the periodic table. So for it to gain a full outer shell, it would need to gain 2 electrons. So when it gains 2 electrons, it would then have a 2 minus charge. So this means then that from each of the sodium atoms that we have, they would each lose 1 electron and give it to this oxygen atom. So let's write that all in words now. The sodium atoms lose 1 electron. The oxygen atom gains 2 electrons. So that means when you have 2 sodium atoms, they form an ionic bond with 1 oxygen atom. Now remember, we want to make it clear that we're dealing with ionic bonding here. Even though we've said it here, what does that mean that's going to happen to these atoms? They actually become ions. And we've put the charges already at the top. So you will get an Na plus ion and an O2, which is oxide ion. Question 3.3. Sodium burns in a gas jar of oxygen. Figure 3 shows the apparatus. So we've got a container with a spoon in the center, and that's holding a ball of hot sodium. Inside of the container is oxygen gas. So you want to write down 2 observations seen during the reaction. So 2 things that we're going to see during this reaction. Well, if it's hot sodium and it's surrounded by oxygen, we're expecting this sodium then to react with the oxygen. Now, when sodium reacts with oxygen, we form white smoke. Now, this white smoke appearing is actually for any metal that's in group 1. But specifically for sodium now, a certain color will appear when the sodium is alight. Now for sodium, the flame color is always going to be yellow. So recalling now, for each of our metals that we find in group 1, what are the flame appearances, flame colors for them? 3.4. Describe 2 differences in the observations if potassium is used instead of sodium. So just like above, we recall that for sodium, it will be a yellow flame. But for potassium, because it's a different metal now, it's going to give us a different flame color. So potassium, we need to remember, is lilac. So the differences will then be a lilac flame will form. But what will be the second difference? Well, as I said, for any metal that's in group 1, a white smoke will appear. However, how's that going to be different when it's potassium now? Well, using our periodic table, we have to identify the positions of these metals in that group 1. Now, if you look at the periodic table, you will notice that potassium is below sodium. So what's the trend in the properties of group 1 metals as you go down the group? The reactivity increases. So we should expect when potassium reacts with this oxygen, we should expect a faster reaction. So this flame that we see is going to appear faster. So that means that the actual potassium will burn faster. Remember that the reason why there's going to be a greater reaction for potassium is because it's a larger atom, so the outer shell is further away from the nucleus, so that means that there's more shielding and there's less attraction of the outer shell electron to the nucleus of the atom, which is positive. Question 4. Group 7 elements are known as the halogens. All atoms of group 7 elements contain protons, neutrons, and electrons. What is the order of discovery of the proton, neutron, and electron? Well, thinking about our models of atoms now. The first model of the atom that we need to be aware of is the plum pudding model. That's the earliest one that we need to be aware of. And in that plum pudding model, there was a discovery of electrons, negatively charged particles that were embedded in a sea or blob of positive charge. So the electrons were first discovered. So we're just left then with our first two, as we know that these bottom two cannot be right. The last discovery in terms of these subatomic particles was the neutron. So that already rules out our first one, so that means that our second one must be correct. Four point two. Table 1 shows the mass of a proton and of an electron. Calculate how many times heavier a proton is than an electron. So if something is heavier, it's going to have a bigger number. But in this case, the way that we can tell that the number is bigger is by looking at the standard form. We can see that it's smaller. Because it's negative, the number should be smaller to indicate to us that it's bigger. So for us to find out how many times heavier something is compared to something else, we need to do division. So in this case, what we're going to do is we're going to take the two values in the table and divide them. So it would actually be 1.673 times 10 to the power of minus 27 divided by 9.109 times 10 to the power of minus 31. And that will give us a value of 1,837 times. A bromine atom can be represented as shown. What is the number of neutrons in this bromine atom? So, looking at your periodic table, remember that the smaller number, for most cases, is the atomic number. And what does this mean? It means the number of protons, but it will also be the same as the number of electrons, because every atom has no charge, because the number of positive and negative charges are the same. The number at the top, which in most cases is the bigger number out of the two, is going to be the mass number. And what that will represent is the total of protons and neutrons in the atom. So, in this case then, of bromine, this means that it has 35 protons 35 electrons, but the total number of protons and neutrons together would be 81. So for us to find the number of neutrons now, it would just mean cancelling out the number of protons that this atom of bromine has. So that would mean we'd need to do 81 minus 35 to find out the number of neutrons. So 81 minus 35 will give us an answer of 46. What's the number of electrons in a bromide ion? They've put in bold ion. As I explained earlier, in an atom, the number of protons and electrons will be the same. So, in a bromine atom, it would be 35 protons, 35 electrons. But in an ion of bromine now, we then have to remember what group this bromine is going to be in. As I told us earlier, it's going to be in group 7. So that means it has 7 electrons in its outer shell. For it to gain a full outer shell, then it would need to gain 1 electron and then have a charge of -1. So if it gains 1 electron and it already has 35, that would just mean that it would be 36. Question 4.5. Chlorine has 2 isotopes. Table 2 shows the percentage abundance of the 2 isotopes of chlorine. Calculate the relative atomic mass of chlorine. Give your answer to 2 decimal places. So for this question now, we're trying to find out the relative atomic mass. For us to do that, we need to take into account these percentage abundances, but the other thing that we would need to take into account are the mass numbers of each of our isotopes. So for finding the relative atomic mass, we need to take the mass number of our first isotope. I'm going to start with the one at the top in the table, which will be 35 chlorine. So our mass number is 35, and we're going to multiply that by the percentage abundance, which would be 75.77. We'll then add that to our next isotope. So we're going to do the same thing, but for the second isotope. So the mass number is 37. We're going to multiply that by the abundance, which is 24.23. Now, doing all of that, you'll come out with an answer of 3,548.46. However, what we need to do now is we need to take into account this percentage. Because if you remember in the question, the values that were given to us were percentage abundances. So to do that, we need to divide this value that we've calculated by 100. So dividing that by 100 now, we should come out with an answer of 35.48 to 2 decimal places. Now, a nice way for you to know whether you're on the right lines or not is if you take the element that you're dealing with and then you find its actual mass number in your periodic table that's given to you. If your value is not very, very close to the value that's in the periodic table, then that means you've made a mistake somewhere. So if you go to the periodic table now and you find a value for chlorine, you'll remember that the value is 35.5. Look at the value that we've calculated. It's very, very similar to that. So that means we know we're on the right lines. (4.6). Figure 4 shows the outer shells in one molecule of chlorine. Complete the dot and cross diagram to show the electrons in the outer shells. So again, what must we know? Chlorine and what group it is. It's in group 7, halogen, just like previously. We need to only show the electrons in the outer shells. So for chlorine then, if it has 7 electrons in the outer shells, we want to show that. So it's 1, 2, 3, 4, 5, 6. And our 7th one would need to be in the middle because we are sharing electrons with this other chlorine atom. Why do we need to share? Because we want both of these atoms to have a full outer shell, and that is covalent bonding. So we put our electron in the center there. We then do the exact same thing for our other chlorine atom, but this time we can use dots. And that would also mean that our 7th electron for this chlorine atom would also need to be in the middle, and then that means that we've done it correctly.